Hi, this lesson is all about using fossils to date rocks. And it's tied in with an idea that geologists call correlation, making links between rocks they find in very different places in terms of how old those rocks are. For example, if you go to Ogmore, you can find very distinctive coral fossils called canina. Now, I've seen those exact same fossils in rocks on the west coast of Ireland in a place called Sligo. Because those two fossils are found in those rocks so far apart, hundreds of kilometres apart, we can tell that those rocks must have been laid down at the same time because they contain exactly the same fossils. Let's look a little bit at how this works. If you look on page 6 of your booklets, you'll find this diagram. This diagram shows us the changing diversity of life through geological time. The wider the shaded bar, the more diverse that particular group of animals or plants actually is. That means the more species that there are. If it narrows, diversity is decreasing. If it's getting wider, the diversity is increasing. So you can see from this that different groups of animals have existed for different periods of time. We're going to look a little bit more at the history of this in theme 10 when we look at fossils. But for now, what I want us to do is to have a look at sort of the big picture that we can get from this. How we can use these fossils to identify points in geological time. Okay, what I'd like you to do is have a go at question 3 on page 6 of your theme 9 booklet. Press pause now, use that graph and see what you can work out. Okay, let's see what this graph actually tells us. The first question asks which period had abundant echinoids and bivalves, but with a low number of brachiopods, with gastropods becoming more common, so they're expanding, and the gymnosperms, the cone-bearing plants, decreasing rapidly. Now, the period that best matches that description is the Cretaceous. Question B had corals, brachiopods and bivalves increasing. Trilobites and graptolites being very common. Echinoids then, those are sea urchins, starting to appear. The period that best matches that is the Ordovician, particularly because of the appearance of the echinoids. Question C is a period with abundant spore-bearing plants, brachiopods, bivalves and cephalopods, corals though declining and trilobites declining very rapidly. That's a description of the Carboniferous. Question D asks for the period which is the rapid expansion of fish and tetrapods, reduced numbers of cephalopods and the greatest numbers of angiosperms, the flowering plants. That period is the Paleogene, Neogene and Quaternary. In your booklet it may say Quaternary and Tertiary. Tertiary is an outdated term now. We don't use it anymore. I'm sorry, that's in your booklets. I need to update those. Okay, those of you that had to go at digging deeper, I asked to try and identify periods of mass extinction. Now, mass extinction is where we see a reduction of diversity in lots of different groups. So it's going to be parts on this diagram where we see, if you like, a pinch in the width of these bars. And where that happens in more than one group, that's an indicator of a mass extinction. So if we look at where these are, we see geological time punctuated by 5 biggies, 5 big mass extinctions at the end of the Ordovician, the late Devonian, the end Permian, the end of the Triassic, and the end of the Cretaceous. The one you'll have heard of is the end of the Cretaceous. That's when the dinosaurs died out, apart from the birds. The biggest one, though, is the end of the Permian. Again, we'll look at this in more detail in the next lesson, in the next theme. Sorry. Okay. For fossils to be useful to tell time, they need to have a number of different key properties. We call these types of fossils zone fossils or index fossils. An example there of an ammonite called Siloceras planorbis, we actually can find that in the Jurassic rocks around the Glamorgan coastline. It's that fossil that tells us that the Jurassic period has started. Anyway, for a fossil to be useful as a zone fossil, it needs to be easily recognised. We've got to be able to identify it. It needs to have existed for a shorter period of time as possible. We want these things to evolve rapidly and then become extinct fairly rapidly. The shorter that time period, the more accurately we can define the time at which a rock that we find it in must have been deposited. We need to have fossils that are preserved easily. They need to have some hard parts, shells, teeth, something that will preserve. A worm, for example, won't be a good zone fossil because most worms are just going to rot. We won't find a record of them in the rocks. They need to be widespread. It's no good having a fossil that's only found in one particular location because we can't make a link with anywhere else. And finally, it needs to be pretty abundant. We need to find lots of these things. They need to be relatively easy to find. For example, T-Rex. T-Rex should make a really good zone fossil. It only existed for a short period right at the end of the Cretaceous. It's very easily recognised. Okay, so it fits a couple of these, but it's only found in North America, and there are very, very few of them. We've literally only found a handful of specimens of T-Rex. All the ones you see in museums are all replicas. So these key properties, which are really important and are asked very frequently in exams, are really important to understand so we can assess whether a fossil will be any use to us. Now, at the bottom of page 7, I've given you another question here. This question, it's illustrating an idea, I suppose. We've got a sequence of rocks here, and we find different fossils in different parts of this sequence. The first question is to say, can we divide this into zones based on the fossils? Let me show you what I come up with for this. What do you think it should be? So we've got a zone at the bottom there. Where do you think the other zones would be on this cliff? We've got another one there, and the final two there. Don't worry about the species names, you do not need to know them. Okay, so if we're dividing up this cliff in terms of time like that, you can see though that the beds don't follow that. The beds are different. What can you work out then about how these beds were laid down? If you look at the one, for example, the shale bed I've labelled X, Y and Z, how do you think that was laid down? What do the fossils tell us about the timing of the deposition of that bed? I'll let you work that out. Perhaps some of the answers will become clearer to that in our next lesson. Okay. Fossils can be really useful for dating rocks, and particularly because we can identify them. We don't need any fancy machines or any high technology. What we need is a good geologist's eye. But we do need to be able to recognise what the key features are that allow us to use those fossils for dating. I'm going to show you next lesson how we can actually apply this to a real life situation, and then we're going to move on after that to look at particular fossils that are useful. I'll see you then.